Welcome to term 3, guys. I hope you enjoyed your recess and I hope you are ready to learn. Okay, so today we are going to look at trigonometry and we'll look at the last part, two-dimensional problems. Now let's quickly jump into it. So first, what we need to recall is that up to so far we have been working with examples such as these ones, whereby let's say you are given a right angle triangle and sometimes you are given you have two known sides, right? Whereby let's just say this is 3 and this is 4, and provided that this is a right angle and that's r. When you are given two sides, in order to find the missing side, which is the hypotenuse, you just use the Pythagoras theorem, which tells you that x squared plus y squared should give you r squared, right? Yes, and that's according to Pythagoras theorem. We have our x, which is 4, so we'll have 4 squared plus our y, which is 3, which gives us 3 squared, and that's equals to r squared. So this is 16 plus that, which gives us 9, and that's r squared. 16 plus 9, which is 25, and we have that our r is a positive value, is the square root of 25, which is equals to 5 units, right? So r is 5 in this case. Or in some instances whereby you could be given a right angle triangle with one known side. Let's say you have this side as 12, let's say 12 centimeters, given that it's a right angle triangle with this angle being 25 degrees. Now they ask you to find x and r. So this is where you use your trig ratios. If you recall your abbreviation, the SOHCAHTOA, right? Whereby you just have to identify that if I'm referring to this angle, then that side over there has to be my opposite, and this side has to be my adjacent, and the longest side has to be my hypotenuse. So in order to find x, since I'm given the opposite and I'm trying to find the adjacent, I will use tan, which means that tan 25 will give me the opposite, which is 12, divided by the hypotenuse, which is x. And then finally I have that x is equals to 12 divided by tan 25. Or when I'm looking for the hypotenuse, again I'm still given the opposite side, and now I'm looking for the hypotenuse. Which trig ratio relates the opposite and the hypotenuse? That has to be sine, right? So sine of that angle, which is sine 25, is equals to the opposite side, which is 12, divided by the hypotenuse, which is r. And then when we make r the subject of the formula, we have 12 divided by sine 25, right? And then we're going to solve this using our calculator and find the exact numerical value. But this only works if you look at both examples. Here you are given a right angle triangle, and even for this one. But that's not the only type of triangles we have. What if now they give you something like an acute angle triangle, something that looks like let's say you are given a triangle that looks like this. Let's take something like that. It's no longer a right angle triangle. Let's say it's a triangle whereby we have an angle here being 25 degrees, and let's say we have 70 degrees there, and you are given at least one side to be 7 centimeters. How are you going to get that side? First of all, we can see that this is not a right triangle. It's not a right angle triangle, right? Which restricts us. Simply, it restricts us. We can no longer use the SOHCAHTOA thing. This only works whenever we have right angle triangles. So in this case, that fails. Can we use the Pythagoras theorem? Yes or no? We can't use the Pythagoras theorem because this is not the right angle triangle. So both of them fail. What if we have to find x and y in this case? We can't use any of these two, right? Then that takes us where? It takes us to a new topic, which is, firstly we are going to explore the sine rule, right? So according to the sine rule, it says that in any triangle APC, so triangle APC looks something like that, provided that it's not a right angle triangle. In fact, even if it is a right angle triangle, but this applies to all triangles, including right angle triangles. So in any triangle APC, the side that is opposite A is going to be small a. The side that is opposite B is going to be small b. The side that is opposite C is going to be small c, right? So that's the naming. That's how you name the sides of any triangle, right? So now it says that a over sine a. So the angle, it says the side over sine of that angle. So it's a divided by sine a. So it's the side, it's always a combination. It's the angle and the side is equals to what? if we relate b and that, it's going to be small b divided by sine of b, right? Sine b, capital B, which shows it's the angle. And then for c, again, c, big C and small c, remember this is the angle, so it's the side which is small c divided by sine of c, which is the angle itself. Or you can twist that around and say it's sine a divided by small a, which is equals to sine b divided by small b, which is equals to sine c divided by small c. But it always has to match. A always has to go with small a, b always has to go with small b, and c always has to go with small c, right? So that's what the sine rule says. Now we'll jump into the proof of that, which tells us that, first of all, in order for us to complete the proof of this is what we need first. We need any triangle. Let's take this kind of triangle. Say I have a triangle like this. Now, right, remember, what am I trying to prove? I'm required to prove that sine A over A is equals to sine B over B is equals to sine C over C. Or you can just twist them around, right? A over sine A, which is equals to B divided by sine B, which is equals to C divided by sine C. But remember, this is small c, right? So let me just, make it a bit smaller there. Something like this. So the first thing we always have to do when you try to prove a theorem, construct, right? Or say we have A, we have B, we have C. Remember, the side opposite to A, small a, side opposite to B, small b, side opposite to C, small c. So we are going to construct. What are we going to construct? We are going to construct a certain height. We are going to construct AD, right? Such that we are going to construct AD such that D lies where? Lies on BC. And also AD should be perpendicular to BC. So this is what I mean by that. We are going to construct a perpendicular height where the perpendicular height is supposed to run from A all the way to BC, right? With D on BC, just the statement says, right? And since it's a perpendicular height, we have a 90 degrees there, right? Just like it says there. Then we are going to let something. We are going to let AD be our height H. And then if you look at this now, it's now separated into two right angle triangles. The first one, which is orientated this way, we have a right angle triangle that looks something like that, whereby, what do we have? We have A, we have B, we have C. Remember, no, it's not C, it's D. We have D here. Remember, this side is H, this side is C, right? But we don't know this. It used to be A, the whole of it, but now we've just bisected it, right? Yeah, so then what do we do now? We are going to apply our trig ratios, since this is a 90 degrees. So if you look at this, the sine of B is equals to what? Is equals to the opposite divided by the hypotenuse. It's going to be the opposite divided by the hypotenuse. So this is B, that's the opposite. So it's H divided by the hypotenuse, which is C. If we make H the subject of the formula, we have H, which is equals to C sine of B. Again, we can do the same for the other triangle now, because we have two right angle triangles. The other one, which is orientated like that, whereby here we have A, we have D, we have C, right? Whereby this is H, and then we have a 90 degrees here. This is H, this is B. We can apply, we can use our trig ratios here on C. Now, if we say sine of C, we get opposite divided by the hypotenuse, so it's H over B, right? If we make H the subject of the formula, we have H, which is equals to B sine of what? Sine C, not small c, big C. And then from here we have two expressions of H. Now we have the first one, which says H is equals to C sine B, and then we have the second one. So we can just equate those two. H is equals to H, so we have C sine of B, which is equals to B sine of C, right? And then we identify the coefficients. We have C, we have B. So we are going to divide both sides by BC. So when we divide this side by BC, we divide this side by BC. The C cancels that, the B cancels that, then we have what? Sine of B divided by B, which is equals to sine C divided by C, small c. So at least we have the first part of it. Now we need to prove for A. In order for us to prove for A, we need to go back again, but this time around we are going to use a different construction. So Again, we have the very same acute angle triangle, assuming this is my acute angle triangle again. So what do we have? We still have A, we have B, we have C, right? And then we have this side is C, this side is B, this side is A. And then what did we say we are going to do? We're going to construct again. But now what do we construct? We construct, let's call it a CE. We are going to construct CE such that, right, such that E lies on what? Lies on AB. Lies on AB. And CE is perpendicular to AB, right? So what I mean by this is that we are going to construct a perpendicular height now that runs from there all the way to that point. Let's say, yeah, somewhere there. Then we have a 90 degrees here, and then this is E. And then again we let something. So now we let what? We let EC equals to, let's call it K now. Let's call this one our height K. Then we have two right angle triangles. If you look at it, we have the top part which is orientated something like this, whereby this is A, this is E, we have K here, and then we have C, we have B. Again, if we apply the sine of that angle there, since this is a 90 degrees here, we're going to have sine A, which is equals to what? Opposite over hypotenuse, right? The opposite is K, the hypotenuse is B. Make K the subject of the formula, we have K, which is equals to B sine A, right? And then from here, what do we have? We have the other triangle, and again we're going to do the same thing on the other triangle, the one which is orientated something like this, something like that now, whereby this is E, this is B, we have A here, we have K, and then we have C, right? And a 90 degrees there. We can apply the sine of B now. We have sine B, which is equals to the opposite, which is K, divided by the hypotenuse, which is A. So when we make K the subject of the formula, we have K, which is equals to A sine B. Again, same process as the previous one. What do? We equate the K's because we have two expressions of K. So B sine A is equals to what? Is equals to A sine B. Identify the coefficients again. The coefficient is B, the coefficient is A. So we are going to divide both sides by AB. So divide by AB, divide by AB. Right, and then what do we have? We have that this cancels that, then we are left with sine A divided by A this side. And then this cancels that, we are left with sine B divided by B. But now let's go back to the previous expression we have. We had something of sine there, sine B over B is equals to sine C over C. So when we take this expression right here, drag it to the side. When we take that expression, that one there, okay, let me keep on dragging it, and then we compare the two. Look at it. It says that, let's call this one A. A is equals to B here. But here it also says that B is equals to C. If A is equals to B, but B is equals to C, it simply means that A is also equals to C. In fact, they are both equals to B. That's why we can now merge the two expressions to get what? To get the final expression, which is sine A divided by A, which is equals to sine B divided by B, which is equals to sine C divided by C. Remember, we can change this into A over sine A, which is equals to B divided by sine B, which is equals to C over sine C, right?